Hello, here we go with some questions on electric fields. We start here with an electric field always exists around a charged particle. Explain what is meant by an electric field. So an electric field is a region where charged particles experience a force. Where charged particles. We don't have to say electrically charged particles because they've just said charged particles in the question. So we can say experience a force. And you could say an acceleration. We are in the world of classical physics, so no problem there. Then state one difference and one similarity between the electric field of a point charge and the gravitational field of a point mass. So a difference, I won't bother writing all this out because it takes too long, but a difference is that gravitational fields always attract mass together. Electric fields can attract or repel. So that would be a good difference to go for. If you're going to have a similarity, you could say, well, we could talk about the inverse square relationship between the force and the distance. So we could have that. You could say they're radial fields. That would be another one you could pick. So there's a few options there. Part C, figure 1.1 shows the uniform electric field between two vertical parallel plates, A and B. Right, so A must be positive, B must be negative because that's the direction that the field lines are going. Potential difference between the plates is 6 volts. Electron or kinetic energy 4 electron volts fired. All right, it's fired into the gap. So it's going to get repelled here by B. Describe and explain the subsequent motion of the electron in the space between A and B. Weight of the electron has negligible effect on its motion between the plates. Right, so we're not getting some kind of projectile element on this as well. We can ignore all of that. So we can say, right, the electron will be repelled by B or attracted, and or you could put both down, attracted to A. Therefore, there will be a force to the left. Therefore the electron will slow and it will come. Will it get to the other side? No, it can't get to the other side because to cross a 6 volt gap we're going to need 6 electron volts and we've only got 4 electron volts. So it will slow and instantaneously, that's too long a word, stop 2/3 of the way across, and then it will reverse direction, then reverse direction. Okay, so that's all good. There's got to be more to this question than that, and there is. Right, so part D, which looks quite involved. 2 different minerals acquire opposite charges when they're crushed into tiny particles. These oppositely charged mineral particles fall from a conveyor belt through a uniform electric field between 2 vertical plates. Right, okay, yeah, so it's coming along here, dropping off all the positive stuff. Oh, it's even saying the positive stuff's moving off here to the negative plate. Negative stuff's going the other way. Okay, fair enough. Potential difference between the plates is 60 kilovolts. Right, I haven't put that anywhere, so let's put that in big red characters up there. Separation between the plates, 25 centimeters, that's included. Length, 1.8 meters, that's included. We've got a 1.2 meter per second terminal velocity of these particles falling between the plates, so I can get rid of that. And then we've got the charge and mass of each particle. Right, so we do have a couple. There's quite a lot of information there. This is going to be quite a few calculations, I think. Calculate the horizontal electric force experienced by a positively charged mineral particle as it falls between the plates. Okay, right. Well, the first thing most people, or certainly me, think of when you start thinking of these electric fields and force, somewhere we're going to need E equals F over Q. Trouble is, we don't have E. We've got Q for a particular particle, as in this 1.5 times 10 to the minus 13 coulombs. We need another way to get E, because we've only got one of these 3 things. We've got 2 parallel plates with a potential difference across them and the gap. So we can use E is V over D. for the electric field between two parallel plates. So that is 60,000 divided by, so a quarter. So we've got 4 times that. So E is going to be 240000. And then we need to multiply that by Q. And then we've got our force. So Q is 1.5. Well, actually, let's go 3/2. That's going to be a lot easier in this case. Times 10 to the minus 13. So 3/2. So we'll have 36. So let's go 3.6. That we've got 1 10, 2, 3, 4, 5 tens. So 10 to the minus 8 newtons. Right, that's fine. Where are we? Last part then. Calculate the horizontal displacement of a positively charged mineral particle after a 1.8 meter fall through the... Yeah, okay, we've got no horizontal drag forces. How far has this positive particle moved off to the right, dropping that far? So if we're doing 1.8 meters at 1.2 meters per second, then that's going to be 1.5 seconds that we've got. So we've got a force of 3.6 times 10 to the minus 8 newtons for 1.5 seconds. That's going to be our impulse. So we've got an impulse is equal to, what's that going to be? Well, I've got to add on half again. So we're adding on another 28. So that's 5.4 times 10 to the minus 8 Newton seconds. So our change in velocity is going to be the impulse divided by the mass, because of course the impulse is a change in momentum. So that is 5.4 times 10 to the minus 8 divided by 8 times 10 to the minus 7. Okay, so let's get rid of lots of things here. Well, actually, let's roll up. If we add a quarter onto 5.4, then we've got that over 10, haven't we? We're adding a quarter on top and bottom, so that would be, what's adding a quarter onto that? 0. And then take the 10 off is the other thing that I'm thinking. So that would be 0.675, and we've still got a 10 to the minus 1 left. So 0.0675. Obviously use a calculator in the exam, but yeah, we don't really need to in this working on here. So that's the change in the velocity, and then the change in the displacement is the average velocity multiplied by the time. So the time was 1.5 seconds. So we've got 3/2 multiplied by the average velocity, which is half of that, 0.0675. So 3/4 of this. Wow, okay. Actually, we'll probably be all right doing this, because 3/4 of 0.06 is 0.045. And then 3/4 of 75 is about 56, isn't it? So that would be plus 0.0056. Add those together, gives you 0.051. So 5.1 centimeters to 2 significant figures. Again, double check that on the calculator if you wish. Yeah, I suppose a lot of people probably wouldn't do this on the impulse route. I find people don't tend to use impulse very much. They'll probably do, I reckon the most common way people do this is do an F/m to get an acceleration, and then do S equals ut plus half at squared, which I'm not a big fan of. It's not particularly elegant. If they've already walked us down to having an impulse, here's a force and here's a time, then why not show that you know what an impulse is? You don't have to have any of these manufactured crank the handle equations. You can just keep away from your SUVAT, as I always like to do, or nearly always like to do, and just deal with impulse and understanding what velocity and displacement are. So yeah, that's a really nice question, that. Really nice. Right, what else have we got? I'll do one more in this. Oh, this is going to be drawing on field lines. So we've got a negatively charged sphere, positively charged plate, draw a minimum of 5 field lines. Right, okay, so we're drawing these in right angles from surface as best you can. Each line has to come out at right angles, or at least look as though you're trying to draw it out from right angles. They get less fussy on mark schemes about what's happening at the sphere compared to what's happening off of the plate. You could mark on that these things are right angles, just to be clear. I mean, you could do the same here as well. Then the field lines are going to go from positive to negative. So you want to get right angles, you want to get field lines. You don't want to draw the lines going into the sphere. You want to make sure they stop at the surface. Right, there's got to be more to this question. And there is. Figure 1.2 shows two positively charged particles A and B. Point X, magnitude of resultant electric field strength due to the particles is 0. Okay, state with a reason which of the two particles has the greater charge. Okay, well, if the 0 point is closer to A, then B must have greater charge. It's further away and is having the same influence. But we need to give a reason, as it says in the question. So let's come back then to our definition of electric field strength, which is F over Q. And we know what our force is. So we're going to end up getting here, because force is our Q times Q over 4 pi epsilon 0 r squared. That's our F. We divide out the Q's. So we've now got E is proportional to the charge over r squared. So if so we can say, well, E is the same at X for A and B, but B is further away, or farther away, I should say, farther away. So i.e. R is greater. Therefore, Q at B must be greater. Must be greater. So yeah, we're just again, it's that usual chain of reasoning. You set up some kind of equation or proportionality and then say, well, this thing is the same for both. That thing is greater than B, so that thing must also be greater than B, otherwise E wouldn't be the same. So chain of reasoning. Right, on figure 1.3, sketch the variation of the resultant electric field strength E with distance D from the particle A. Right, okay, so our electric field strength, I mean, this is telling us, so it's telling us what direction the particle is going. If we got a positive charge in there, you can see this is going to change though, and if we put a positive charge in this area here, it's going to move towards X. If you put a positive charge on the other side of X, it's going to move towards X. Yeah, these positive charges are going to get pushed away by both A and B. So the direction of the electric field is going to be opposing each other. They're going to oppose on either side of X. One way is going to the right and on the other side is going to the left. So we need to use both sides of the axis here. We also know that the electric field is stronger near to B than it is near to A because we've got more charge at B. So, we've seen here that the electric field strength is proportional to that charge. So we need to have a greater field strength at B than we do at A. Right. So which way we decide is going to be positive doesn't really matter too much on this, as long as we can either say, well, it's negative here and then positive there, or the other way round. So let's go with it being negative and positive. We got a smaller value here at A than we have at B. I mean, B is what, 7 squares away. A is 3 squares away. We've got this 1 over r squared going on here. So yeah, I mean that's quite a big difference. With them having the same effect there. I mean, we've got for the 1 over r squared, we've got a q over 9, so that's the charge at A divided by 9 is equal to the charge at B divided by 49. So we've got 5 times the amount of charge at B that we do at A. So that's quite a big difference. So let's go for a large positive, or as large as they allow on these axes at B. We know we've got to go through 0 point at X, and then we're going to have a small value at A. And then how are we going to actually connect these things up? Well, I mean, it's not going to be a pure 1 over r squared because we've got 2 overlapping fields here, which are combining together. But yeah, it's not a straight line with the way that I've drawn those crosses. So let's do something sort of resembling a 1 over r squared and do something like that. I don't think they get that funny about that in mark schemes in terms of the shape of the graph. Yeah, the key things that you've got here is you're using both sides of the axis. So you want one bit to be positive, one bit to be negative. You want it to go through the x-axis here at X, and you need it to be larger in magnitude at B than it is at A. They're going to be your 3 marks that you're getting out of this. I don't think they're going to be that fussed. If you'd just drawn a large value, a small value with X in the middle and drawn a line through, don't think they would have had that much problem with that. I could be wrong, but don't get too bogged down on it. But we're used to having it as 1 over r squared, and it's going to be looking like that. Yeah, we're not going to have it flat over here coming out, like flat as in straight coming out of B with a small effect of A 10 squares away. So I'm going to draw them as curves. Right, last part then. To round all this off, we got figure 1.4 shows a stationary positively charged particle. That's a pretty unexciting figure 1.4. This particle creates both electric and gravitational fields in the space around it. Explain why the ratio of the electric field strength to the gravitational field strength at any point around the charge is independent of distance. Right, well, we've already spoken about this. This is because, so we got both E and G are proportional to 1 over r squared. So when we take the ratio, so in ratio of E over G, 1 over r squared cancels. Therefore, ratio independent of r. Independent of r. Right, yeah, we've already spoken about that before. Yeah, it's one of the many similarities between electric fields and gravitational fields, the 1 over r squared variation. So there you go. That was, yeah, they were quite nice questions, those all in all, I think.